New robots are being designed to share spaces with humans. Strong, dangerous cage robots will become obsolete at some point in the future. But these robots that share spaces with humans need to be very carefully controlled, especially when collaborating with elder or disabled people. In order to solve this issue, robots need to exert the minimum force possible in order to be safe while fulfilling task requirements. In this line of work, we have implemented variable impedance Cartesian controllers, which are controllers in the Cartesian coordinate space that make robots capable of modulating their rigidity and strength throughout motion. We can, for instance, set a rigid behavior of a robot in certain directions while the robot behaves softly in others. This allows to, for example, create artificial walls that the robot cannot cross according to a learned pattern of precision requirements. Moreover, let's say that we learn a motion task where part of the motion requires to be very precise. Then the robot will have high gains in that moment. But this can also be combined with parts of the motion where the robot does not care much about precision. In those segments of motions, the gain will be lower. Thus, the robot will exert less force and interaction with a human will be smoother. Also, we can control the redundancy of a robot as we like. An additional feature that we created on these controllers is that a task space can be represented in a lower dimensional space. Controlling the robot in such a lower dimensional space leaves some artificial degrees of freedom uncontrolled, and we can take advantage of such situation in order to achieve secondary tasks, such as obstacle avoidance. But how can we use all these advances for cloth manipulations? In controlling cloth garments manipulated by robots, new challenges arise, partly due to the uncertainty on the cloth state. However, we still want to keep a controller behaving safely while fulfilling the cloth's desired motion. Therefore, we need to use prior knowledge of cloth's dynamic in order to improve manipulation capabilities, but also need to be able to update such beliefs and integrate visual and or force feedback into the control. We then use model predictive control, which computes the control action on the robot as the action that will maximize the similarity between the motion of the system, a cloth garment, and our desired reference. In our application benchmark, we assume that we have a piece of cloth represented by a mesh, and we want to control the position of the lower corners of the cloth by acting on the upper corner's position. Using such model predictive controllers, we can track the reference signal with good precision, either in one-dimensional motions, two-dimensional, or three-dimensional motions. And even with large deformation motions, the controller is capable of following the reference trajectory. These controllers are now being tested in real robot scenarios, where computational restrictions are an important element. Therefore, we are also studying methods for encapsulating the prior knowledge of cloth dynamics in smaller dimensional spaces, such as Gaussian process dynamical models.